Hello everybody and welcome back to Math 251. I hope you're having a wonderful day. Yeah, let's go ahead and get right into it. So last time we talked about the notion of a limit. We did a couple of examples where we introduced the limit. We talked about secant lines versus tangent lines and how these are related to limits. So today's lesson, we will define what it means for a function to have a limit. But before that, we have our mathematician of the day and our math history fact of the day. So today's mathematician of the day is Srinivasa Ramanujan. He was a 19th century Indian mathematician who, despite having almost no formal training in mathematics, made substantial contributions to the field. The movie The Man Who Knew Infinity is about his life and tells the story about how he believed God was showing him the math. It's an excellent movie. I definitely recommend it. And did you know that the equal sign was invented in 1557 by a Welsh mathematician named Robert Recorde? Before that, they would just write the expression is equivalent to. So I'm very glad that the equal sign was invented. All right, so like I said, today we are introducing the definition of a limit. And this definition is pretty dense, so I just want to warn you about that. But once we get into it, hopefully it should not be too much trouble. So here is the definition of a limit. Suppose we have some function f, and it's defined really close and possibly at the point that we are going to call a. A is the point that we care about. So we have a function that is defined for all values x near point a, except possibly at that point. Then if f of x, the y value, this is the y value, is arbitrarily close to another y value that we call L, for all x sufficiently close to, but not at the point A, then we write the following. This definition says that the limit as x approaches A of f of x is equal to this letter L. And we read this as the limit as f of x, the limit as x approaches A of f of x is equal to L. That is how we read this. So I know this is a pretty dense definition, but once we do some examples, hopefully it won't be too bad. So in the first example, we want to use the following graph to determine the following values if possible. In part A, we want to determine f of 0 and the limit as x approaches 0 of f of x. Well, if I look at my graph, I can see that when x is equal to 0, f of x is equal to 3. So f of 0 is equal to 3. In order to find the limit as x approaches 0 of f of x, I have to look at where my function is headed, both in the positive and in the negative directions, towards 0. So if I look at this side of 0 right here, I'm on my function f of x, and I am on the right side of 0 on my function going towards the point 0. I can see that on this side, my function is approaching the point 3. And if I look on this side of the function, again, on the left side of 0, on the function f of x, I also see that that side is approaching the point 3 as well. So this means that the limit as x goes to 0 of f of x is equal to 3. So in this case, f of 0 and the limit as x approaches 0 of f of x are the same values. They're both 3. In part B, we want to determine f of 1 and the limit as x approaches 1 of f of x. So if I look at 1, I see that this point right here is telling me that my function is defined at that point, at the x value x equals 1. So f of 1, in this case, is defined at 2 because of that point discontinuity there. But then in order to find the limit as x goes to 0, as x goes to 1 of f of x, I have to do the same thing that I did in the previous example, and I have to look at both sides of the function from the right and from the left as x approaches 1. So on the right-hand side, right, this is where x is equal to 1. So if I approach the function from the right, I see that it approaches the y value of 4, and it's doing the same thing on this side. If I approach x equals 1 from the left, I see that the y value approaches 4. So the limit as x goes to 1 of f of x is equal to 4. And we have one last example, f of 2 and the limit as x approaches 2 of f of x. Well, we see on our function that here I have the x value 2, and it is defined to be 5 on our function. So f of 5 is, f of 2 is equal to 5. F of 2 equals 5. Then the limit as x approaches 2 of f of x. Well, if I were to draw this line out, right, this line continues this way, then I can pretty easily see that if I were to approach this x value of 2 from the right, then the y value approaches 5. And if I approach the x value 2 from the left, that y value also approaches 5. So this is equal to 5. So what do these examples tell us? Well, the limit of a function at a particular point is not always the same as the value of the function at that point. So we saw this in part B of this first example, right? Here in part B, the limit was 4 as x approached 1, but the function evaluated at 1 was 2. These two y values are different, and that's okay because the limit will not always be the function evaluated at that point. I also want to emphasize that the limit here, we have 3, 4, 5. These are always y values. So maybe I'll make a little note here. Limits are always y values. Because we will always have the limit as x approaches a certain number. So when we evaluate a limit, it will always be a y value. All right, next we are going to go into another definition. This is called a right-sided limit. So this is just another flavor of a limit. So suppose we have f defined for all x near a. This time x has to be greater than a. Then if f of x is arbitrarily close to L, again, L is a y value, for all x sufficiently close to a with x greater than a, then we write the following. The limit as x approaches a, and then we put a little plus sign here. That means from the right of f of x is equal to L. We read this as the limit as x approaches a from the right of f of x equals L. So this is just on one side of x, right? So if I were to, oh my gosh, I'm so sorry. Oh, there we go. If I were to draw a picture of this, so if I had a graph and I had a function, then if I wanted the limit of this function from the right, then I would only be looking at this part of the graph. And then we also have the analogous left-sided limit. So here we have f is defined for all x near a with x less than a. If f of x is arbitrarily close to L for all x sufficiently close to a with x less than a, then we write the limit, as x approaches a from the left, so we put a minus sign there, of f of x is equal to L. So in this case, we have something like a graph here. And if I cared about this x value right here, a, then the left side limit would only be looking at this portion of the graph here. And we'll be doing an example here in a couple minutes where the right-sided limit and the left-sided limit are not the same. All right, let's do an example. Let f of x equal x cubed minus 8 over 4 times x minus 2. We want to use tables and graphs to make a conjecture about the values of the following if they exist. So if you would like, you can pull this up on Desmos, but I am going to draw a picture of this graph. So this graph looks something like this. So it kind of looks like a parabola, except it has a hole right here at the point 2, 3, because that is where the denominator of this fraction is equal to 0, so it's undefined there. All right, so let's look at the following. We want to determine the limit as x approaches 2 from the right of f of x. Okay, well, I'm looking at the right-sided limit, so I need to look at this portion right here. As x approaches 2 from the right, I need to look at where my f of x is going. And I see that f of x is approaching this y value 3. It doesn't matter that it's undefined there. All I care about is that it is approaching the point 3. All right, then we'll look at the limit as x goes to 2 from the left of f of x. So here we want as x approaches 2 from the left-hand side, so we are going to be approaching this side of f of x. And again, this is also approaching the y value of 3. And then if we look at the limit in general, the limit as x goes to 2 of f of x, well, kind of like we did in this very first example, right? I looked at the left-sided limit and the right-sided limit, even though we didn't know what those were called, and they were the same, so I just called the limit in general those points. So here, the limit, because the limit as x goes to 2 from the left and the right is 3, the limit in general is 3. Because the limit as x approaches from the left and the right of 2 of f of x is 3. So let's note that even though f of 3 is undefined, is undefined, the limit as x goes to 2 of f of x is defined. That is all right. So we kind of have this theorem that we've been using in part C of this problem, and now we are going to state it explicitly. So this is the relationship between one-sided and two-sided limits. So assume f is defined for all x near a except possibly at a. Then the limit as x approaches a of f of x equals this point L if and only if the limit as x approaches a from the right of f of x equals L, and the limit as x approaches a from the left of f of x equals L. So the limit as x approaches a in general of a function is only equal to that number if the two-sided limits agree with each other. So if we go back up to this example, B, then these two limits don't agree with each other, right? Oh wait, no, sorry, excuse me, they do. I'm thinking of a different example, sorry. Scratch that. Okay. Let's do this example, number 3. So we want to find the values of the limit as x approaches 2 from the left of g of x. So this is our g of x. Oh, sorry, I meant to fill this in. We want to find the values of the limit as x approaches 2 from the left of g of x, the limit as x approaches 2 from the right of g of x, and the limit as x goes to 2 of g of x. So let's first look at the left-sided limit, the limit as x goes to 2 from the left of g of x. So x is approaching 2 from the left, so I need to follow this strand right here, and I can see that as I get really close to 2, my y value is approaching 3. So this is equal to 3. The limit as x approaches 2 from the right of g of x. So now I'm approaching 2 from this side of our function, which means I have to look at this side. And I can see that this strand right here is approaching the y value of 2. So in this case, our left-sided limit and our right-sided limit do not agree with each other, right? They're not the same. And according to the theorem that we just talked about, if these two limits do not agree with each other, that means that the limit as x goes to 2 in general of, of g of x does not exist, because the left-sided limit and the right-sided limit do not agree with each other. We often shorten this to D and E, does not exist. That is, again, because of this theorem right here, the relationship between one-sided and two-sided limits. So the limit only exists if the left-sided limit and the right-sided limit are the same number. Since they were not the same number in this case, our limit does not exist. So this was a relatively short lesson on limits. I know that we did cover a lot of material though. If you are still stuck on limits and kind of what they mean and how to find them, I would recommend trying the My Math Lab homework for this section. The more examples you practice with this kind of material, the more you can understand it. So I definitely recommend doing it on My Math Lab. As always, don't feel hesitant to reach out to me via email. I am more than happy to answer your questions. I hope you have a great day, and I will see you next time.